Okay, so in the last video we looked at the human eye and saw how an eye can change its focal length in order to focus an image at the retina. But before we go forward, I think I should comment on the difference between focus and resolution. If an object is far away, we may not be able to discern details about that object no matter how good our eyes are. So it's just that the object is too far away, or more precisely, the angle between the two details that we're trying to see is too small. This is caused by interference between light that travels through our eye, and we'll discuss this a bit more in our next unit. But the thing we need to know here is that the resolution limit for the human eye is about 0.02 degrees. That's the angle between the two things that you're trying to see. Has an angle of 0.02 degrees or less, then your eye will not be able to see the difference between the two. It doesn't matter what the distance is. So if you put your hand out and stick out your thumb can cover up a large object that is far away. If you want to convert to radians, you would multiply by 2 pi over 360, so the angle in radians will be about 0.00035 radians. So the distinction that I'd like to make here is that if the angle between two things is so small that you can't distinguish it, that is not necessarily an issue with your eye. It may be an issue with the nature of light. What is an issue with your eye is if it cannot form the focal length necessary to project an image onto your retina. That is an issue that can be fixed with corrective lenses. So to think about this, we'll look at two dots and figure out what is the maximum distance at which our eye would be able to distinguish the two dots. We would be able to tell them apart. So our two dots are 1 centimeter apart, and the resolution of our eye is 0.02 degrees, or 0.00035 radians. So if we draw a right triangle, so as shown here, so the opposite side is y, the 1 centimeter, or the 0.01 meters, and then the adjacent side of the right triangle is the distance, so that's the thing we are trying to find. That means that the sine of theta is equal to the 1 centimeter divided by the distance, and so if we want to be consistent with our units, we might switch to meters. So that means 0.01 meters, and then divide by the sine of 0.02 degrees, or the sine of 0.0035 radians, and we get that the distance when we do this, when we do the algebra, is 28.6 meters. Notice if you do the sine, so on the slide here we've done the sine of 0.00035, you'll notice that the sine of 0.00035 is equal to 0.00035. The point is, at very small angles, the angle in radian is pretty darn close to being equal to the angle in radians. So yeah, so I've been a little loose with switching between degrees and radians here, so be careful with that. So one convenient thing here is, so if you just use radians, that means you can then just jump from sine in radians is equal to the angle in radians, but that's only true at very small angles, so be careful with that, but in problems like this one, that works well. But if you want, you can just always use degrees. Just take the sine of 0.02 degrees. That'll give you 0.00035, and you'll be able to solve the problem just fine. Just be careful, right? Make sure you're consistent with your degrees or radians. In any case, we've found that 28.6 meters is at that distance, a very good set of eyes can distinguish between two dots that are 1 centimeter apart. So this isn't an issue with your eyes not being able to strain to see it. You're just trying to see something that is too small to resolve due to the way of nature of light. So you have a few problems to do like this, except it will be the lights of a Jeep or the print of newspaper, but I think it's pretty much the exact same problem. I also should mention I haven't discussed diopters, so I've bumped the question from the last set to this one, and I think you'll need it for one of these questions. So the diopters of a lens is equal to 1 divided by the focal length, and the focal length is in meters. So if you have a question about that, you convert the focal lengths to meters and then divide 1 by the focal length. So this is kind of a common way of keeping track of lens sizes. All right, good luck.